Good morning, guys. Today we're going to look at some different theorems or properties about the roots of polynomials. First one we're going to look at is called the Fundamental Theorem of Algebra. You can read what it says. The part that's most important to us is where it says every polynomial function of degree n greater than or equal to 1 has exactly n zeros, including multiplicities. So what that means for us is a 7th degree polynomial better have 7 zeros. Or 7 roots. Well, remember, those words, zeros and roots, are kind of interchangeable. And if we're talking about real zeros and real roots, then we can classify them as x-intercepts also of the polynomial. Now, 7th degree polynomials should have 7 zeros, and whether that be one zero that has a multiplicity of 7, or whether that has 7 unique zeros. That's what the including multiplicities means. So the degree of the polynomial corresponds to the number of zeros for that polynomial. Very, very important thing when we're going through and hunting for all the zeros or roots of a specific polynomial. The next two deal with irrational and complex numbers. Now, we know that everything we've been working with, we've had real number coefficients. A real number coefficient comes from taking all these real number roots that contain real numbers and multiplying them together. That's the writing a polynomial as a product of its linear factors, what we have been working with. So if I want to get real numbers, I typically multiply together real numbers. Now, if I have a root that is complex, meaning it's got an I in it, or if a root that's irrational, meaning it's got a square root in it, but our final polynomial does not have i's or square roots in it, we know that that had to have been canceled out somewhere along the multiplication process, where we distributed and combined all those like terms from multiplying those linear factors. So, to cancel out an irrational number or to cancel out a complex number, an I, we have to multiply it by its conjugate, as we've looked at before when we explored imaginary numbers. So, that's what the irrational conjugate root theorem and complex conjugate root theorems say. To have real coefficients or rational coefficients, we have to have canceled out the i's or square roots, and we do that by multiplying by the conjugate. So if we know we have a plus b square root of c, then it's implied a minus b square root of c also has to be a specific root. And that kind of goes back to our how do we get irrational or complex numbers. And that's, in these scenarios, that's by solving a small equation. That's by setting it equal to 0 and solving. And at some point, you're going to take the square root. Well, square roots, when we inject that square root into the problem, they come out as plus or minus pairs, those conjugate pairs. So if we have plus the square root, then we know minus the square root is implied. And the same goes for the complex numbers. If we know we're given plus bi, or a plus bi, then the a minus bi is implied. So it's just fun talking about different ways to know what roots you have, how many you're working with, and what you have depending on what you're giving or what you already know about the polynomial. Give me a couple seconds and I'll get some problems up here and we can explore these two and how they fit back with this one. So guys, here we have an example. I want you to take these roots and write a polynomial that would have had these roots. So let's just look and think of how do we get roots. Well, we get roots by setting factors equal to 0. So it's kind of just working this whole process backwards. So if I get roots by setting factors equal to 0 and solving, we know that each of these is the solution to a small equation. So we know this is x equals negative 2. We know this is x equals 0 multiplicity of 2. We know this is x equals 3 halves and x equals negative 3 plus square root of 2. Well, using the irrational root theorem, I also know that I have an implied root here. If I have plus the square root of 2, I also have to have negative 3 minus the square root of 2. Okay, remember, square roots will come in their plus or minus pairs. So the irrational root theorem tells me that this implies this. The existence of this one implies the existence of that one. All right, so now we look at it. How many roots do we have? I've got 1, 2 here, so that's 3, 4, 5, 6 roots total. So if I've got 6 roots, we know we should end up with a 6th-degree polynomial. Now let's go through and actually turn these back into linear factors. So x equals negative 2, we got that by subtracting 2 from the other side. Remember, we factor, set each factor equal to 0 and solve. Well, here's the solve. Now we need to work them back to be equal to 0. So if I add my 2 back over, I get x plus 2 equals 0. That was one factor. This one, you add 0 over, we know doesn't do anything. So we know that multiplicity of 2 means that that occurred twice. So we got x equals 0 2 times. So that's what 0 multiplicity of 2 means. On this one, how did we solve, or how are we going to unsolve that one? Well, it's just reverse order of operations, correct? So I'm going to move the 2 back over first. So I'm going to multiply the 2 over. So that's 2x equals 3. I'm going to move the 3 back over. So that ends up being 2x minus 3 equals 0. So there's another factor. Now over here, I've got to move the 3. So plus 3. I've got to move the square root of 2 minus square root of 2 to make it equal 0. Same over here. Move the 3, move the square root of 2. So I've got x plus 3 and plus square root of 2 equals 0. So we still get that plus or minus. So we got 3 plus square root of 2 and 3 minus square root of 2 and 3 plus square root of 2. So these are all my linear factors. Those are all of the linear factors. And we just want to put all those together back by just multiplying to get the polynomial. So if I take x plus 2, x, 2x minus 3, x plus 3 minus square root of 2, and x plus 3 plus square root of 2. All of that together should equal my polynomial, which we'll call f of x. From here, it's just distribute and combine like terms. You can decide how you want to do that. I'll show you how I would group them. Let's clean it up a little bit first. I'll put my x's out front. X and x is x squared. X plus 2, 2x minus 3. And then down here on the end, x plus 3 minus square root of 2, x plus 3 plus square root of 2. We'll wait and we'll do the x squared last. We'll just tag it on the very end. So when I group these two together, I get 2x and x is 2x squared. 4x and negative 3 is plus 1x. And 2 and negative 3 is negative 6. Now down here is the trinomial. You're just a product of trinomials. So we just take it 2 at a time. So x and x is x squared plus 3x plus square root of 2x. Now we'll distribute the 3 plus 3x plus 9 plus 3 square root of 2. Just trying to keep our like terms lined up. Negative square root of 2x. Negative 3 square root of 2. And that'll be negative 2. So as you can see, why the plus or minus pair, that conjugate pair, is important because it takes the square root of 2 portion and causes it to cancel out, which means we'll have only rational coefficients in our polynomial. So when we clean that up, x squared times 2x squared plus x minus 6, x squared plus 6x, 9 minus 2 is 7. Then from there we just keep distributing and combining like terms Okay, and I'm just going to kind of show you what the end result should be. It should come out to give us 2x to the 6th plus 13x to the 5th plus 14x to the 4th minus 29x cubed minus 42x squared. So that's what our final polynomial should be after we finish distributing, combining like terms, and doing all that happy stuff that we have in here. So that's the process. I'm not going to waste your time right now showing all the mechanics of distributive property. I really wanted to show it here so you can see why the conjugate is so important to cancel out those square roots and leave us real number coefficients or rational number coefficients. Give me 1 second and I'll get one up here for you guys to try. Okay guys, here you go. Here's an example that I want you guys to work. Take these roots and write a polynomial that's not the exact polynomial because we could have multiples of the polynomial, but write a polynomial that would have these roots, and I will wait right here. Okay, hopefully you've had an opportunity to work that and get a solution. Let's check your work and see how you did. First thing, let's look for implied roots. So we have the -1, that's rational and real, we're good there. -2/5, rational and real, we're good there. The 4 plus 3i is not real, it's imaginary. So we know that it has an implied conjugate root of 4 minus 3i. Remember, conjugate means opposite the square root portion. So just the 3i becomes opposite. Now we'll set each one equal to 0, x equals -1. Multiplicity means do it twice. So multiplicity of 2 means do it twice. X equals -2/5, x equals 4 plus 3i, and x equals 4 minus 3i. Go through, put them back as linear factors, so I'm going to add the 1 back over. So that's x plus 1. Add the 1 back over, gives me x plus 1. Multiply the 5 over, and then add the 2 over, so that's 5x plus 2. Remember, check your order of operations there. On this one, I've got to subtract the 4, subtract the 3, so that's x minus 4 and minus 3i. Subtract the 4, subtract the 3, subtract the 4, add the 3, so it's x minus 4 plus 3i. And we just start combining them together. I'm going to put these two together, so I'll put my 5x plus 2 on the outside. When we put those two together, we get x squared plus 2x plus 1. It's just your perfect square trinomial. I'm going to show you a little different way to look at this. We could look at this as x minus 4 minus 3i and x minus 4 plus 3i. So x minus 4 minus 3i and x minus 4 plus 3i. So we could look at that like a difference of two squares situation. A plus b times a minus b, and we know that's equal to a squared minus b squared, just from all of our experience of factoring differences of two squares. So that's what you get when you multiply conjugates. When you multiply conjugates, you get the difference of their squares. So if I look at this as my first term minus the second and first term plus the second, I can treat that as x minus 4 squared minus 3i squared. And that works for all conjugates, whether they're complex conjugates or irrational conjugates. Well, where that helps me out is that's a perfect square trinomial situation, so we know that that would be x squared minus 8x plus 16, and 3i squared, we should know, is -9, right? 3 squared is 9, I squared is -1, so -9. So minus -9 gives us +9, so that we get 5x plus 2 times x squared plus 2x plus 1 times x squared minus 8x plus 25. And from there we can go through and distribute, combine like terms, and hopefully you were able to get 5x to the 5th minus 28 x to the 4th plus 38 x cubed plus 230 x squared plus 209x plus 50. So again, I'm not going to waste your time showing you distribute and combine like terms. You know how to do all that stuff. So this implied root, getting them written as linear factors and being able to combine those conjugate pairs is really the newer stuff that we don't have as much experience with. From there, it's distribute, combine like terms. Should get that polynomial. And remember, we always have a way to check these by comparing the graph or table of our answer back to the graph or table of our product of linear factors, see if they're the same, or just graph that and see if it has those as its x-intercepts. And obviously we wouldn't see the imaginaries as the x-intercepts, but you can check what you can see to give you an idea if you're on the right track. And we'll look at that how to check again in class tomorrow. But that's how we take given zeros or given roots, identify any implied roots or zeros, and then turn that back into some scalar of the actual polynomial that fit those. I've got one more thing I want to do with these theorems about polynomials. So if you give me a second, I'll get that up and we will look at that. So here's the next test we should be able to perform at this point. I should be able to use this given root to find all roots of the polynomial. Well, think about what technique we always use to find roots right now. To find roots, we factor, set each factor equal to 0, and solve. So if I want to find all the roots of the polynomial, then it means I want to factor this polynomial. So I'm going to use this given root to factor the polynomial. Well, it's the same thing we've done before. Use it to identify all factors. If I'm given a factor, we divide by that factor. Well, this factor is a little bit different than some of the ones we've divided by in the past. So what we're going to do is we're going to pair it up with its implied root. So if I know x equals -1 minus 2i, then I should also know that x equals -1 plus 2i. So Fundamental Theorem of Algebra tells me there are how many roots to this polynomial? There are 5. Well, we already know 2 of them. One was given, one is implied, so we need to find the other 3 by dividing this into this and taking that remaining cubic, because I've got 2 x's here, so it's going to be a quadratic. So take that quadratic, divide it into this quintic, and we should get a resulting cubic, and then we can solve cubics. Remember, we always use this idea of I've got to get it down into something I know how to factor. So something small enough for me to factor, whether that be by the groupings or cubes or squares or quadratics, whatever we're doing, I've got to get it down to that point. So we're going to use these two. Well, how can I use those two, get the given root and the implied root, to get something I can actually divide with? Well, it goes back to what we just did. We're going to put them together and find what polynomial, what small quadratic equation had this as its solution, as its roots, and then that's what we're actually going to divide by. That's the factor we're going to work off of. So let's put together x equals -1 minus 2i and x equals -1 plus 2i. So as we do this, move the 1, move the 2i, move the 1, move the 2i. So I get x plus 1 minus 2i, and I get x plus 1 plus 2i. Oh, let's flip that. We can look at it as we did before. X plus 1 squared minus 2i squared, correct? These are just a product of conjugates. So it's the first term squared minus the second term squared, which is x squared plus 2x plus 1, and 2 times I, the 2i quantity squared is going to be 4i squared, so -4. So minus -4 is plus 4. So we get x squared plus 2x plus 5. So we know this quadratic is one factor of this polynomial. Well, to get the other factor, we just divide. Well, when we're dividing by a quadratic, we know we've got to use long division. So x squared plus 2x plus 5 divided into x to the 5th, 2x to the 4th, 5x cubed minus 8x squared minus 16x minus 40. And we just go through our long division steps. First divided by first, multiply, subtract, repeat. So first divided by first. X to the 5th over x squared equals x cubed. So let's throw x cubed up there. Then we multiply. We distribute that x cubed. So x to the 5th, 2x to the 4th, 5x cubed. Subtract. So draw your line, change your signs. X to the 5ths cancel, 2x to the 4ths cancel, 5x cubes cancel. All right, now we need to bring down enough terms to be able to keep dividing. So negative 8x squared minus 16x minus 40. And then we repeat, because x squared can divide by x squared, so that means we get to keep going. That, and we haven't got a remainder of 0. Remember, these are factors we're talking about. So it should all divide out and it should give us a remainder of 0 if we have set things up correctly. So that's kind of your constant check as you go. So first divided by first, we're repeating our steps. Negative 8x squared over x squared is negative 8. Distribute that. Negative 8 times x squared to negative 8x squared. Negative 8 and 2 is negative 16x. Negative 8 and 5 is negative 40. And as you can see, when we subtract, we draw our line, change our signs. Everything cancels, no remainder. So that means we put these together correctly and we divided correctly. So what we're left with is x cubed minus 8. That's our remaining factor. So this is one factor, that's the other factor. Now we need to solve that. How do we solve an x cubed minus 8? Well, we recognize it as a sum of two cubes. So we're going to set it equal to 0 and solve. Remember, I'm not going to just add the 8 over and take the cube root, because that gives me x equals 2. That's only one of the roots. We know a cube root, a third degree polynomial, should have 3 roots. So we've got to recognize it as a difference or a sum or difference of cubes and factor it appropriately. So just going through your sum of cubes steps again. Erase this. Give us some room to work. So x cubed minus 8 equals 0. Got to think of it as x cubed plus negative 2 cubed. Correct? First base cubed plus the second base cubed. Then we put it into our format. First base plus second base times first base squared minus the two of them together plus the second base squared. So that's just going back to your sum of two cubes factorization. Clean it up. X minus 2, x squared plus 2x plus 4. Set each factor equal to 0. So x equals 2. Well, we knew that one from the x cubed minus 8. Here, x squared plus 2x plus 4. And we solve that one by a quadratic formula. So we get x equals negative b plus or minus square root of b squared minus 4ac all over 2a. So we go through negative 2 plus or minus 4 minus 16 is negative 8. Keep working. Square root of negative 8 is 2i square root of 2 over 2. All three positions can reduce by 2. Just remember your rules for that. So we just divide everything and we get negative 1 plus or minus, that's 1i square root of 2, but we want to write it in complex form, so the I goes on the end. So if we're going to write all of our zeros, we have x equals 2, in addition to the one we were given, the one that was implied, and negative 1 plus or minus square root of 2i. So that is all 5, 1, 2, 3, plus or minus makes 4 and 5, all 5 roots of this polynomial. Again, we can check that a little bit if we'll go and graph this on our graphing calculator. Graph the original. The 2 will show up as our only real root, our only x-intercept, because these 2 were imaginary and those 2 were imaginary. So we get a little bit of the check that we can do with the calculator on this one. Okay, give me a second and I'll put one of these up here for you guys to try on your own. Okay guys, take a few minutes, pause the video, try to work this one out where you use this given root to identify all of the roots of this polynomial, and I will wait right here. Okay, now hopefully you were able to get a solution to this. Let's check your work and see how you did. So first thing we're going to do, take our given root. It's irrational, so we know that we have an implied root that goes with it, and that would be, if I'm given positive square root of 2, negative square root of 2 is implied. From there, I'm going to take those 2 roots, write the polynomial, the small polynomial that gave me those 2 roots, because that's the small factor that we're going to then divide with. So I've got x equals square root of 2 and x equals negative square root of 2. So we move those square roots over. So x minus square root of 2 times x plus square root of 2. Distribute, combine like terms, or recognize it as a product of conjugates. X squared minus square root of 2 squared. So that's x squared minus 2. Okay. So that's our factor that we're going to work with. So we're going to now do long division from here into here. So x squared, remember put zeros in for missing terms. I don't have a linear term here, so I need to put a 0x in there to hold that place value. Let's see what we have. 3x to the 7th minus 12x to the 6th. Tell you what, I'm going to do one thing before this. Before I do my division step, I'm going to look and see, are there any common factors I can pull out of this, just to make my number smaller and easier to work with. So I can recognize that every single term up here multiplies by a factor of 3 and has a factor of at least x cubed. So if I take 3x cubed out, that leaves me x to the 4th minus 4x, 3 and 3 is 3, just hang on with me. Minus 7x squared plus 8x plus 10. So all that does is just give me a smaller, easier to work with function. It also tells me that 3x cubed is one of my factors. 3x cubed equals 0. So x is equal to 0 multiplicity of 3. So I've already identified out of the 7 polynomials, 3 right there, 2 right there, so that's 5 polynomials, or 5 roots identified, so there's only 2 left. That tells me that once I divide, I should have a quadratic left. So let's go through and do our division now. So x squared plus 0x plus 2, we're going to divide that into x to the 4th minus 4x cubed minus 7x squared plus 8x plus 10. If you didn't recognize the common factor here, you could do it on the next step. When you actually go through your factoring step. But the sooner you realize common factors, the easier life gets. So we go through our division steps. First divided by first, multiply, subtract, repeat. So first divided by first, x to the 4th over x squared equals x squared. So there's that quadratic that we know should be remaining. Distribute that. X squared is x to the 4th. X squared and 0 is 0x cubed. X squared and 2 is 2x squared. Subtract. Draw your line, change your signs. X to the 4ths cancel. Negative 4x cubed. Negative 9x squared. Bring down 3 terms for 3 terms and repeat. First divided by first. Negative 4x cubed over x squared to negative 4x. Multiply then subtract. So negative 4x times x squared is negative 4x cubed. Negative 4x times 0 is 0x squared. Negative 4x times 2 is negative 8x. Subtract, so we draw our line, change our signs. Those cancel. Negative 9x squared plus 16x plus 10. That should be a minus 2 right there. See, there's x squared minus 2, so x squared minus 2. So as we go through, that should have been a minus 2, changes to plus, so that gives us negative 5. So negative 5x squared. That should have been a minus 2 again, so that would have been make that negative 8x. Negative 8x and 8x gives us the 0. So now we're where we're supposed to be. So first divided by first, negative 5x squared over x squared is negative 5. So put negative 5 up here, distribute it, negative 5x squared plus 0x plus 10. Draw your line, change your signs. Cancels, 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 gives us 0. So again, you know you're doing it correctly when everything is canceling out like it should. So that's that constant check you get to look for. Now we just set that remaining quadratic equal to 0. Let's go ahead and write this one up here. All right, so we've got plus or minus square root of 2. We've got 0, multiplicity of 3, and let's see what else we're left with. X squared minus 4x minus 5 equals 0. This is quadratic. We know we solve quadratics either by quadratic formula or factoring. This one should factor into x minus 5, x plus 1. So double check it. X squared is x and x. Negative 5 is negative 5 and 1. Negative 5x plus 1x is negative 4x. So we're good. Set each factor equal to 0. So x equals 5 and negative 1. So 5 and negative 1. So this is all 2, 5, 6, 7 roots of that 7th degree polynomial. Again, we can check by graphing this right here, and since those are all real roots, we can graph that and we can check each one of those and see that those are where the actual x-intercepts show up. Sorry for the mistake right there. It happens. It's a big board. I lose track of numbers sometimes. But that is it for roots, theorems about roots of polynomials. Remember, Fundamental Theorem of Algebra, the corollary is important to us right now. Number of solutions, or sorry, number of roots or zeros has got to be equal to the degree of the polynomial. And if I'm given an irrational or complex root, its conjugate is implied also. That's that, and I will see you in class tomorrow, guys.